Let's continue our session. The next speaker is Delio Mugnolo. The title is The Heat Kernel on Metric Graphs and This Geometric Significance. Please.
Yeah, thank you very much. Thank you for introduction and thank you for the invitation. I have to apologize because when I accepted your invitation, I already knew I couldn't be here every day because of some personal reasons. So thank you for still allowing me to talk here. The topic of my talk today is, it's about the heat kernel on metric graphs. And this is something a bit different from what is known by, I think, many of people, so many of you in the audience, namely spectral theory of metric graphs. It might be that not everybody in the audience is familiar even with metric graphs, so I will introduce them briefly. So, but unlike the usual settings, so spectral theory of metric graphs, which is also what I was talking about last time I visited Mexico City in 2020, right before the beginning of the pandemic, I will not work with eigenvalues, but with heat kernel. I will introduce this in a second. So for those of you who are not familiar with metric graphs are essentially something similar to this structure depicted here in this a photograph of an artwork by an Italian artist. So essentially, metric graph can be thought of as a kind of a collection of tubes, more or less one-dimensional, semi-one-dimensional objects, and a few points, like for instance here, you will have some ramifications. So there is a possibility that several one-dimensional objects join at certain points. So this is the very pictorial imagine you can have of a metric graph. More precisely, and this is what we will need for our talk, metric graphs can be introduced in a formal way as follows. So we start with a collection of edges. And in this talk, I will consider the possibilities that E might be either finite or countably infinite. Each edge will be assigned a certain length, which I denote by LE. So in a certain sense, this set of edges, each of whose can be identified with an interval of certain length LE, forms a metric measure structure of very general kind. So in a certain sense, this is a kind of a pre-graph. It becomes a graph when I start identifying vertices. And this is done as follows. I just introduce an equivalence relation on this set here, which can be, well, the set of endpoints of all these edges. And this equivalence relation will define, in a certain sense, a wiring of this graph. So I can extend this equivalence relation from this set here to the whole of this set here, of this pre-graph. And this quotient space is what we call the metric graph. So the point here, and this is what I know it's a bit technical, maybe even a bit Bourbakistic, but I think it's convenient to convey the message. Once we are given a set calligraphic E, like in this case, there are many possibilities of turning it into a metric graph by attaching or reattaching edges at different points. So for instance, these two metric graphs are essentially two wirings of the same pre-graph. So you see here we have 6 edges. We also have here 6 edges. We can think of all these edges having the same length. And then simply by connecting them in a different way, by considering two different equivalence relations of this set of vertices, then we will have 2 different metric graphs. And one of the leitmotifs of my talk will be to understand whether there are certain topologies which are optimal or which maximize or minimize certain functionals, as we'll see. Okay, so because we can introduce the Lebesgue measure on each of the edges and the shortest path metric on this quotient metric space, it's possible to introduce both a space of continuous functions on a metric graph and also canonical Lebesgue space and LP space on G. And once we have these two spaces, of course, we can also introduce a Sobolev space. So this is simply the set of all functions which are continuous across the metric graph with respect to the shortest path metric or topology, and also are in L2, so square integral, with a weak derivative, which is also in L2. And of course, as soon as we have an L2 space and an H1 space, we can start playing. So we can consider, in a more or less canonical way, a quadratic form, which is simply given by this. So I integrate over this metric measure space G the derivative, weak derivative squared of a function. And well, it turns out that this is, with this domain here, this is a closed quadratic form. This is something that has been observed by Serge Nicaise in 87, but it was probably known even earlier. So this was for the finite graph case, and Bercolec and Kuchman observed the same also for a certain class of infinite graphs, namely under so-called bounded geometry condition, which means what I've written here on top of my slide. So the edges, oh, sorry, I think there is a typo here. So what I mean here is that the infimum of the edge length is bounded away from 0, and the supremum of all these edge lengths is uniformly bounded. Okay, and then once we have a closed quadratic form, there is a self-adjoint operator on L2 associated with it, and this we call this Laplacian on a metric graph. So this is a very natural concept, and people have started working and doing analysis on this operator already in the 80s. What's interesting for my purposes is the fact that this quadratic form is not only a quadratic form, not only closed, but in fact it is a Dirichlet form. Well, of course it's symmetric, as you see, but it's also Dirichlet form. And it's even reducible if the metric graph is connected. So for those of you who are not familiar with the theory of Dirichlet forms, this means that the operator associated with the form A, so this Laplacian, generates a Markov semigroup on this space here, on the Hilbert space L2. So the heat equation is well posed. Okay, so this can be seen also in different ways. Under reasonable assumptions on the graph, you can construct a fundamental solution of the heat equation more or less directly, for instance, by Fourier methods. So we are going to work with the heat kernel. So what's the heat kernel? Let me remind you, let me recall, the heat kernel is the fundamental solution of the heat equation, meaning Pt dot y is the function depending on this space variable, which I denote here by dot, that satisfies this initial value problem for the heat equation. This is a general object that can be defined in many different contexts, domains of manifolds and so on. So in general, there is no heat kernel. So one has to prove that this is defined, this is existing. One specific easy case where this is can be done is if we know that the Laplacian in general, the operator that governs this evolution equation, has pure point spectrum, because there in this case there is something called the Mercer theorem that delivers an explicit formula for the heat kernel in terms of eigenvalue and eigenfunction expansion. And so in particular, we can see in this way that heat kernels are certainly existing and associated with Laplacians that are, so if the Laplacian has Dirichlet conditions on an open domain, or if it has Neumann condition under slightly more restrictive conditions, so it has to be Lipschitz boundary. This also holds for smooth compact manifolds without boundary, and so on and so forth. So there are a lot of cases where heat kernels can be constructed. So in our case, we want to introduce them for metric graphs. Luckily, it's not something I have to do with myself, because this is already something which has been proved by Roth in the 80s. So he showed that for a finite graph, there is a heat kernel. So it's easy to see by linearity of the semigroup that this is precisely the integral kernel of the semigroup. So in particular, this formula holds. This is a general property of heat kernels. And due to certain nice properties of metric graphs, you can even show that in this case, the heat kernel is a bounded function. So in fact, you can show even a bit more. You can show that the heat kernel is even Hölder continuous. This is something I recently proved with my doctoral students, Patrizio Bifurco. So this was proved for finite graphs. Cattaneo extended these results to infinite graphs in the 90s. And the proof is very easy in this case, in the case of graphs. You only have to observe that the form domain is continually embedded in the space here. Oh, sorry, here should be a G, so infinity of G. And then what's in the sometimes called Kantorowicz-Wulik theorem, sometimes the Danforth-Pettis theorem. Anyway, something characterizing the existence of an integral kernel for operators mapping L1 to L infinity, so, which is exactly what happens here. So far, so good. So I'm going to discuss the properties of this heat kernel for metric graphs. So for these purposes, I would like to present or to recall a formula for the heat kernel due to Roth. And in order to present this formula, I need a bit of notation. So if you have a metric graph, then it's possible to arbitrarily orient every single edge of this graph. So let's call this orientations a bond. We can associate with each bound an initial or a final endpoint, which we denote in this way. And two different bonds are consecutive if the final endpoint of one is the initial endpoint of the next one. Okay, a directed path is, as you can imagine, just a sequence of consecutive bonds, starting, say, at a vertex B and ending at a vertex W. And we denote the set of all possible directed paths between B and W by this notation here, so by calligraphic P of VW. Okay, so this is all we need to introduce an explicit formula for the heat kernel. So if E is finite, then Roth showed in the 80s that a heat kernel can be written in this way here. So we have a certain normalization factor, and then the heat kernel is given by a series where you have certain coefficients alpha p weighted by an exponential that decreases very quickly. Now, the point here is that the set of paths, oriented paths between x and y is an infinite set, because you are allowed to go back and forth as often as you wish. So you touch a vertex and then you can go back, for instance, and then over and over again. So it's an infinite set. So this is an infinite series. But the point is that the more often you go back and forth at vertices, the longer your path become. And therefore, this exponential becomes very small. So essentially, only very short paths can really be seen in the series. Very long paths that happen if you're making random walk in a certain sense in your graph, then become very small and they can be negligible, hopefully. Nevertheless, this makes this this series very hard to study on a combinatorial level. So I still should tell you what these alpha p's are. So these are so-called transmission coefficients, or sometimes scattering coefficients. These are given by a product along all vertices that appear in a path of these terms beta here. And the scattering terms here are defined in this way. So essentially, if you're scattering to a point that is directly, this term is always -1. And if it is not a directly vertex you are touching, so a vertex where you're imposing directly condition in a graph, then you have two different possibilities. Either either you are bouncing, so the bond EK is the reciprocal of EK plus 1. And in this case, you have a 1 here. Or otherwise, you only have transmission, so this term disappears and you have something here. So you have 2 divided by the degree of this vertex, so the number of edges incident in this vertex. So this is something very classical. This was proved by Roth. Roth could only prove this formula for all internal points of a graph. And very recently, both with Harrell and Jones extended this formula also to any point of the graph, including the vertices. So this is a absolutely convergent series for any 2 points in the metric graph. So for instance, so in this specific case, so this is a metric graph. So if we consider if you want to consider the value of the heat kernel between point V and W, among all other possible paths we have to consider, there is this one. So we first start with this edge, then we go back, then we go farther, and then we reach W. So this is one possible path, and the scattering coefficient alpha p is simply given by the product of this term here. So the scattering coefficient this point, and then at this point, and then at this point again, and then here. So this is a directly vertex, and this is not a directly vertex. So this is why if you just apply the definition I was showing before, then you end up with a value 2/9 for the scattering coefficient of this path. But the problem is that you have to consider infinitely many of them. So this makes everything a bit complicated. So bookkeeping is a bit cumbersome. Okay, so let me just mention that also for the case of infinite graphs of boundary geometry, it can be proved that Roth's formula extends. So this was shown by Cattaneo for the case of equilateral infinite graphs, and by Simon Becker, Federica Gregori, and myself for the general case of infinite graphs. Okay, so the heat kernel is a very nice object. So there is a lot of analysis that can be performed on the heat kernel. Usually this is done on manifolds. So there is a whole community working on it. Let me just mention the name of Grigorian. But so one of the typical things you want to prove is that there are some nice estimates from above or below in terms of the heat kernel of the Gaussian semigroup. So these are usually called Gaussian estimates. And in case of general manifolds, there are sufficient and necessary conditions for getting Gaussian estimates. In the case of graphs or metric graphs, this has been proved by myself in 2007 for finite graphs, and this has been extended to infinite graphs by Hesseler so more or less 5 years later. So basically, you can prove that something like this holds. So this is interesting because this is a very powerful estimate. So I will not show any consequence of it, but there are several spectral and some properties in spectral theory and analysis of evolution equation that depends on this estimate. This estimate can be proved by, or I have proved it by, it's called Davis tricks, something that Brian Davis introduced in the 80s. And it's interesting because it seems that even though there is an explicit formula for the heat kernel, which is Roth's formula, it's not clear whether this Rhodes formula can be used to deduce estimates like this. So it's actually an open question, an interesting one, I think, whether one can make sense of all this series appearing in Rhodes formula to get an upper estimate like this. Okay, but it's not exactly the heat kernel what I'd like to talk about today, mainly at least, but two different functions. So the first function is probably known to most of you. This is called heat trace. So the heat trace has several different equivalent definitions, but among other things, you can define it like this. So simply the integral of the heat kernel along the diagonal. There is another function which is slightly less popular. It's called heat content. Heat content is the double integral of the heat content, or the heat kernel. Well, in this case on the graph, but you can study, of course, on general domains or manifolds or whatever. So the heat content has been introduced by Davis and Van den Berg in the 80s. And it's very easy to observe, they did it themselves in 89, that semi-good property plus Gaussian estimates for the Laplacian on domains implies that the heat trace can be controlled from above by heat content. So in particular, if the heat content, so because the heat content is always, it's easy to see, it's always bounded from above by the total volume, by the volume of omega, then also a similar estimate holds for the heat trace. So the question is, which they addressed already in 89, and as far as I know, it's still open, is whether it is true that heat trace, the finiteness of the heat trace implies finiteness of heat content. So this is an interesting question. So one of the reasons why people started working with heat content is that these heat content, so there is a very mighty theory of heat kernels. So in a certain sense, it looks like heat content is easier to study by heat kernel methods than heat trace. So it's a nice way to derive bounds on heat trace, and heat trace in turn, as you know, can deliver information on the eigenvalues of the spectrum of an operator. So I was mentioning this conjecture, so that the finiteness of the heat trace implies finiteness of the heat content. This is actually true for a certain class of domains. So if the domain is infinite but horn-shaped, then in fact you can prove that the finiteness of one implies the finiteness of the other one. So this triggered the study of the heat content, and first very relevant result in this direction was obtained by Van den Berg and Gilkey in 94. They proved that the heat content has a short time expansion where the first term is simply the volume of omega, and the remaining terms are powers of square root of t. And people started studying this expansion and finding interpretation for higher and higher coefficients beta k. So essentially, as you can imagine, beta k incorporates information on the geometry of the boundary, so like mean curvature and so on. So there are a lot of people who have been studying this functional. I've mentioned here a few ones. Probably Van den Berg is the one who really made it popular. So, but there are a lot of other people also studying it. So I am working on graphs though. So has this been studied on graphs? Yes, it has. So for combinatorial graphs, so what we had, for instance, in the previous talk, the heat trace had been studied at least since two papers in the 90s by Stark and Terrace and Chung and Yao, respectively. And the heat content has been introduced by McDonald and Myers in 2003. On metal graphs, things are even, so the heat trace has been studied even earlier by Rhodes, as I will show in a second, or in a few minutes. And the heat content has been studied, as far as I know, only a few years ago by Kaladay, Kaganovsky, and McDonald. But not in a geometric sense. So now I will focus on a finite case to show what kind of the flavor of results I am trying to reproduce by means of the heat kernel. So my starting point, also due to my mathematical background, is spectral theory of metric graphs in the finite case. So if the graph is finite, then it's very, very well known that the Laplacian on the graph has pure point spectrum. And let's denote its eigenvalues in this way, so in a growing order. So the lowest eigenvalue is always 0 because the constants are span this eigenspace. And if the graph is connected, which I always assume in this talk, then the second eigenvalue would be strictly larger than 0. And this is an object which has been studied a lot. So let me present a very well-known estimate on it. So this is an isoperimetric inequality first obtained by Serge Nicaise. So he proved that this guy, oh sorry, this is yes. So that this guy here is bounded from below by this number here, so pi square over the volume of the graph square, and this estimate is sharp and rigid in the sense that it is attained if the graph is trivial, so it's an interval, and only in that case. Nicaise also showed that something similar holds if you impose at least one Dirichlet vertex on your graph. In this case, the estimate changes a bit. So Bond and Levy could show that this estimate can be improved if you have information on the topology of your graphs, in particular if your graph is doubly connected as a metric space. So in this case, they could improve both estimates by a factor of 4. Again, these estimates are rigid sorry, it's sharp and rigid. So there are also upper estimates. This has been obtained by James Kennedy, Pavel Kurasov, Gabriela Malinova, and myself, and then in a sharper version with higher information, on the connectivity by Band and Levy again, 1 year later. So if you have a metric graph on a certain number E of edges, then you have this upper estimate. And if you additionally know that the graph is a slightly better connectivity, so it's a tree, then you get an estimate like this. So again, this is something that has been studied by many authors in the last 10 years. So there are a lot of estimates on the first, and so on the first non-trivial and higher eigenvalues of the Laplacian metric graphs. You can, as I was suggesting 1 minute ago, so you can do the same also upon imposing Dirichlet conditions. So you introduce a Sobolev space just the same way as we did before. So imposing Dirichlet conditions, certain subset of vertices. And again, the restriction of the form we're studying before to this Sobolev space is again a Dirichlet form. Again, if you have finitely many edges, then this Laplacian, so the associated operator is pure point spectrum. So and again, the eigenvalues accumulate to infinity, and the lowest eigenvalue is simple and strictly positive. And again, you can associate a heat kernel with this Laplacian. So everything works again. And the nice thing is that we can perform some nice analysis on the heat kernel of this Laplacian and recover a few results that, in a certain sense, have a geometric flavor, just like the ones we were seeing before. So what I showed here was very typical. So results that can go under name of spectral geometry. So connection between the geometry of a certain object, in this case a graph, and the spectrum of the associated Laplacian. And you can do something similar here with the heat kernel. So it's not spectral geometry in a certain sense, it's heat geometry. So connecting the geometry of a certain object and the heat kernel of the associated Laplacian. So we can study the integral of the heat kernel on the diagonal, so this is just a trace, and we can get an upper estimate of this form. This is simply consequence of the Gaussian estimates I was showing before, and a lower estimate like this. This is consequence of called kernel Katz's principle of not filling the boundary. This is something that Postel and Kremen were proving for, in particular, for metric graphs a few years ago. And using these two estimates, we can apply Karamata's theorem and back transform these estimates and show that from these estimates from the trace, you can get something similar also for the eigenvalue asymptotic. So we can recover a Weil's law for the eigenvalues. So in particular, both the Neumann and the Dirichlet eigenvalues of our Laplace on a metric graph suitably renormalize, converge towards pi square over the volume square. So in particular, if we know all eigenvalues, we can recover the volume of our graph. And this is, in general, the only information we can recover if we have the asymptotics of the eigenvalues. So it's possible to show that there is, in general, no further term in this expansion. So it's not possible to recover, for instance, the Betti number or the number of vertices or edges of our graph. So can this be bypassed in a certain sense by using different objects, for instance, a heat kernel? Yes, it can. This is the main theorem I would like to present today. So this is something which has just been proven, I've just been proving with my doctoral student, Patrizio De Fulco. So it will hopefully be uploaded to arXiv in a few days or weeks. So the heat content can be written in this way here. So the heat content, so let me recall, it's the double integral of the heat kernel of this Laplacian here with very clear condition at certain vertex at VD can be written as the volume of the graph minus a correction term including the number of Dirichlet vertices plus another term that depends on a function h, and again this scattering terms I was showing before, and this function h is here. So this is a correction term to x times the RC function. So so Gauss arrow function and the complementary of it. So this is just defined in this way explicitly. So this is okay. RC is a very well studied function, just like Earth is, and this perturbation of Earth is not very hard to study. So in particular, you can show that it maps the real positive numbers to itself, and it's not only strictly monotonically decreasing, but actually very, very rapidly decreasing. So it has this decay pattern here. So the main message here, the take-home message, is that the heat content does not only have this description asymptotically. This is a precise, it's an exact formula. So this formula holds for all times. So this is something which is very rare. So I will show later another formula which is known to hold for all t. But in general, either for graphs or for different objects, for manifolds in particular, there are very few formula which are known to hold for all times. So this is I will show it's a mighty description of heat content. I think I have just I would like to invest a few seconds in the sketch of the proof. So the idea is that you can describe, you can split essentially your heat content in a term that depends only on the heat content of a line on R, which is essentially this first term here, plus a correction term, and the correction term will sum up to, or will be combined to other correction terms that come from the main term, which is the one that includes the topology of the graph, which is this one here. So these are the terms responsible for the heat content independence of the connectivity of graph. So if you change the wiring of your graph, if you attach or cut through vertices, then the transmission, so the scattering coefficients alpha p will change. So this will have a consequence or an effect on your series here. So this is how you see that graph does influence the heat content. Now we can see that because h is such a nicely decaying function, each of these series here, so all these 4 terms here, are converging. So we can play a bit with them, and then there is a longish and tedious combinatorial analysis of each of these 4 terms that allow to show that the sum over the set of all possible paths between any 2 points in the graph can be reduced to the set of all possible paths starting and ending only at Dirichlet vertices, which is just still an infinite set but much smaller, and it's easy to bookkeep because these are the paths starting or ending at a non-Dirichlet vertex yield a vanishing contribution to this series here. So this is the main idea, but again, if you take a look at the paper when we put in archive, then the proof itself is rather long, so it's several pages. So one immediate consequence of, or more or less immediate consequence of this formula is that, so you see you have these 2 main terms in this formula. So if you consider the difference between heat content in these 2 terms, the error term can be estimated by a nice quotient of exponentials that can be seen like here. So in particular, we recover an asymptotic, a short-time asymptotic of this form here. So you probably recall, so you remember this estimate or these asymptotics by Van den Berg and Gilkey. So this is in the same spirit. The main difference is that they had, in general, they have infinitely many polynomial terms. And in our case, the only polynomial term is this one. So all higher polynomials, polynomial terms disappear. So we only have this exponential decay here given by this object here, depending on the minimal length of an edge in the graph. Another thing that can be started by the heat kernel is, for instance, we can measure the boundary of a subgraph. This is something that goes on the name of Cacciopoli type results. So for domains, or so for subdomains or for submanifolds, this is something that has been studied a lot in geometric analysis in the last, I would say, since the 1950s, since Cacciopoli himself. In the case of graphs, it seems to be new. So what you basically do is you start, so you measure the flow, the heat flow from a subgraph H to its complement, and then you renormalize. So you take the short-time asymptotic and you renormalize, and what you get is the number of vertices in the boundary of this subgraph. So as far as I know, the most advanced counterpart of this estimate for domains is due to Miranda and co. in 2007. Okay, so this is just a starting point, admittedly. So we have this nice formula for the heat content, and now the question is whether we can derive more geometric information on metric graph using it apart from the volume and the number of Dirichlet vertices. So chances are good because people have already done something similar for spectral analysis or using the eigenvalues. So what Bifulco and I were doing was to try to replicate some of the ideas we already, also me and other co-authors already started for eigenvalues, namely what we call spectral surgery. So what happens if we change a graph, if we take a rewiring of a graph, can we say something about eigenvalues? And in this case, we are doing the same for the heat kernel or the heat content. And indeed we can, so let me present a very few results we obtained. So if we lengthen an edge, then there is a Hadamard-type formula. So you can show that the derivative of the heat content with respect to this perturbation of the edge length can be written in this way. So unlike the spectral, so the counterpart for eigenvalues, this is not does not have a fixed sign. So this already suggests that the analysis is much more complicated. What does have a clear monotonicity is the behavior of a graph under a certain class of perturbations, of topological perturbations. So if you attach a subgraph, or if you insert an edge between adjacent vertices, or if you mirror your graph at a certain non-Dirichlet vertices, or if you cut through midpoint of a loop, then you can show that the heat content goes up. So we are going to use this estimates as a toolbox to try to study estimates on the heat content in terms of geometric properties of a metric graph. So maybe something like number of edges, number of vertices, maybe diameter, or more complicated metric or geometric quantities. Okay, maybe very quickly, let me say that so there is a famous parameterization by Peter Kuchment of all possible self-adjoint extensions of the Laplacian on L2. So they can be written in this way, where f is a trace of a function, and f f underline and f2 underlines is the normal derivative. And if there is no Robin term here, so if this r is equal to 0, then it is known that Roth's formula extends to this kind of self-adjoint extensions. It's also known that some of them can generate Markovian semigroups. So we are in a similar setting as in the case of this, as I was showing before. So the question is open whether heat content can be studied also in this general setting. So I was announcing that there is something similar already known, so some exact formula. And this is, of course, the trace formula. So this is something which has been proved by Roth for pure non-Dirichlet conditions in 1984, extended by Nicaise to Dirichlet case, and then constraining Potthoff and Schrader to more general extensions without Robin part. So again, all these three formulae are exact so they hold for all t. So this is, in a certain sense, the counterpart of what I have been doing with Patrizio Bifulco. So yeah, I wouldn't say these formula or our formula are bad. I think they have a similar behavior. They encode similar information, and it's just a question how much you can play with them to try to obtain new properties on these functionals. Okay, so this was only for the finite case, in particular because, of course, you have this term here, both in the trace formula and something similar in the heat content formula. So it's not quite clear what would happen if the volume of G is not finite. There is a few things that can be said in the Bowden geometry case or in the infinite case after all. So let me just mention some results from a paper with Simon Becker and Federica Gregorio. So if we perturb the Laplacian with a potential that is nice enough, then again, you can have a positivity improving semigroup. And if V is the right sign, even a Markovian semigroup, not only on L2, but also on all the spaces here. And you can also describe the spectrum. In particular, 0 is a simple eigenvalue also on spaces of continuous function, which are interesting if you are not doing, say, quantum mechanics, but if you're doing, say, random walks or so stochastic analysis. And the nice thing is that, again, so like in the finite case, is something that has been observed by von Belo in the 80s, and then by Pankrashkin and followers since the zeros. Then you can relate the spectrum of this operator here with spectrum of certain matrices, infinite matrices acting on some suitable so function spaces or sequence spaces. And another consequence of all this theory is that the spectrum of this Laplacian is p-independent, even in this case of spectrum of a bounded geometry, and the Feynman-Katz formula hold if we have certain sub-exponential growth of volume. So what happens if the geometry is infinite after all? So if you allow the edges to have decaying lengths, this is much more complicated, and I think this will be the this will be what I devote the end of my talk to. So if we have an infinite but locally finite graph, then it's possible to introduce a new form with a slightly different domain. So the form is formally the same, but the domain is given by the function in H1 that are finitely supported on this metric graph. So the question is, if you close it up, do you get something essentially self-adjoint? And this has been studied very extensively in a famous paper by Exner, Kostenka, Malamud, and Neidert in 2018. So long story short, what they show is that the essential self-adjointness of the Laplacian on the metric graph is related to essentially self-adjointness of a discrete Laplacian on a combinatorial underlying graph. And then Kostenka and Nicolucci started right away to study spectral properties of the Friedrich extension of this guy here. So what happens if you allow for the graph to support a non-essential self-adjoint Laplacian? Then it turns out that you could have, of course, different extensions, and these extensions can be characterized by something we call edges. So what I'm going to discuss now, or to recall now, is some results I got in the last years with Kostenka and Nicolucci. So an end of a graph, of an infinite graph, is essentially a sequence, a decreasing sequence of open connected subsets that, so that they are, roughly speaking, so that their complement exhausts the graph. So there is the definition is a bit technical, so I will not show this in detail. But let me just mention that a whole zoo of possibilities exist. So there are very natural graphs that can have two ends, for instance, z, or one end, for instance, z squared, or in general, zd, or infinitely many ends, for instance, the binary tree, which has even incountably many ends. So the question is whether you can consider ends as point at infinity and then imposing boundary condition at these ends to characterize the self-adjoint extension of your Laplacian. And this can be done. And in certain cases, you can even show that the Laplacians even have nice spectrum. So this is a nice result that goes back to Bob Carson in 2000. So if the phi total volume of a graph is finite, then you can show that any of these self-adjoint extensions as compact resolvents, so in particular pure point spectrum. And then you can prove, this is what I've done with this group of colleagues, that you can extend to this case also the isoperimetric inequalities I was showing before due to Nicaise. So in a certain sense, the case, so if the graph is finite and behaves in a nice way, in a certain sense, and there's finite volume, then you can define on it a Dirichlet Laplacian and a non-Dirichlet Laplacian, more or less like in the finite case. The point is that even if the finite volume is not, the total volume is not finite, there's been shown by several people that the spectrum can still be purely point, so it's purely discrete. So the question is, what can be said about this case? For instance, the semigroup could be compact. This is something which has not been studied so far, what I can report about is a result I got with Kostenko and Nicolucci. So if the finite volume, if the total volume is finite, and if, which is not always given, if the domain of the Laplacian, of a certain realization of the Laplacian is contained in the Sobolev space here of an infinite metric graph of finite length, then the Laplacian has a heat kernel, and the heat kernel is associated with the semigroup of trace class. So in particular, trace is finite. Let me stress that this is, in a certain sense, non-trivial because a road type kernel formula is unknown. So the only cases so far where explicit formula for the heat kernel are known are only for finite graphs and infinite graphs of bounded geometry, but not for the unbounded geometry case. In particular, we cannot derive trace or heat content formula in this case here. So we need different approaches to prove this result here. So this is okay. You can take a look at our paper to see how we do it. It's a bit tricky operator theoretical proof. I think I still have 5 more minutes, so let me just present or show something very puzzling I discovered in the last year together with my colleagues. So let me show an example of, so I was saying before that you can have pure point spectrum even if your total length is not finite. So let me consider a very specific class of graphs, which we call diagonal CAM. So these are constructed like this. So we attach to an interval certain vertical spikes, and the vertical spikes have the length chosen in such a way that the distance between any two tips of the spikes is always the same. So the diameter of this guy is 2, but we play with the rate of speed of accumulation at this point here. So this is this parameter will be denoted by alpha. So if alpha is very large, then there will be just a very few spikes. But if alpha is small, then we have a very high accumulation at infinity. So if alpha is larger than 1, it's a simple exercise analysis 1 to see that the finite volume of this graph is finite. So in particular, this Laplacian has pure point spectrum by imposing Neumann condition at these tips of these spikes. But what happens if alpha is less than 1? Well, it turns out that we have phase transition. So precisely, so if alpha is between 1 and 1/2, then again, even though the volume is not finite, you still have pure point spectrum. And this suddenly changes at 1/2. So you have phase transition, so the spectrum changes at this point here. At this parameter here changes from pure point spectrum to operator with essential spectrum. And this can be done more or less, can be proved more or less explicitly by constructing a Weil sequence. So but this is still a very puzzling result. So there are still many open questions. For instance, what is the ground state in the case that you don't have, that you have pure point spectrum, but the volume is infinite. So this case here, because of course a constant cannot be a ground state anymore. We also have shown together with James Kennedy and Matthias Teuffer that in this case in between, you have non-Weil asymptotics with a very strange polynomial behavior. Something similar has been observed by fractals, but as far as we know, this is the first case this has been observed by metric graphs. Okay, I think I will not show the proof. So in this case here, with these kind of graphs, very little is known about the semigroup. So it is known that there is a semigroup, but essentially no information on the heat kernel is known. It's not even clear that for all these parameters alpha, there is a heat kernel after all. So I think probably I will skip the very last section. So the torsional geometry, this is probably more technical. So those of you who are interested can take a look at this paper by Marvin Plume and myself, but I will skip it. And thank you for your attention.
Thank you very much for your nice talk. Any questions, please?
May I? Delios, thanks for the nice talk.
Hi, Pablo.
Hi. What I want to say is not a question, rather a thought. You said that you can do the heat content for graphs which have other than Kirchhoff as long as there is no Robin part. Now, but at the same time, you had something with graphs which are Kirchhoff plus a potential. Now it is known that you can at least some non-Robin conditions you can approximate by Robin plus a potential. So I wonder whether one could use this fact to do something.
This is a very good point. I was not studying it so far. So we did. So if the graph doesn't have Dirichlet conditions, right? So then everything is trivial because then the heat content is constantly equal to the total volume. This is easy to see. So at least some decay is needed to get something interesting. So if you impose Robin, you still can define the heat content. What we cannot do so far is to study the heat, to derive the heat content formula. But you're right. So this is something I think this would probably require even more careful bookkeeping. So you have a sequence of graphs.
That's a small set, a small set of Robin. It's the delta where you still keep the continuity. So you have you have the Sobolev space, and there is an extra term, and you can So I wonder whether it could be used.
So we don't have a heat content formula for Schrödinger operators, but because there is a Feynman-Katz formula, then it shouldn't be too complicated to derive a heat content formula for potentials. And then even if the potential is relatively rough, like a delta, then this still should, it might work. So for sure it's a very good idea. Yes. So if the limits can be interchanged in the right way, at least it possibly works. Yeah, thanks.
Okay, thank you.
More questions? So if not, let us thank the speaker for the nice talk. Thank you very much. So our session is over. Thank you for all.
Okay, so